morning. We have been discussing the distance redshift relation. The problem that we are discussing is as follows, that we have been discussing. There is a galaxy which is the source, which emits radiation at some time t emitted when the scale factor has a value a t emitted, and the radiation reaches the observer at some time t observed when the scale factor has a t observed value, which we take to be 1. So, this is at present. So, the radiation from here will be observed at a redshift 1 plus z, z is the redshift, which is 1 by the scale factor when the light was emitted. Now, the problem that we have been considering is to determine the distance in terms of the redshift. The redshift is what is observed usually directly. We would like to determine the distance as a function of the redshift. And it is convenient to work with the line element, cosmological line element written like this. This is the time part, this is the spatial part, the term in the bracket is the comoving distance. We have this coordinate chi. In addition, we have theta and phi which are there inside this. I have not written it out explicitly. Now, this function s square over here, this is okay. The metric is not, line element is not to be written like this, but like this instead. This is a specific form, this is the most general form. So, we have this, oh, theta and phi are here. So, we have this s square of chi. If we have a flat, spatially flat metric k equal to 0, this is the familiar chi square, which is the familiar metric in the Euclidean space, 3-dimensional space, right. If the space is curved, you can have two possibilities, k equal to +1 and -1. This we have seen as a 3-dimensional sphere, it is a closed space, it is a compact space, the 3-dimensional sphere. In this case, this function takes on this form L square sine square chi by L. If it is a negative curvature, space of negative curvature, k equal to -1, this is a hyperboloid, this is a space of this is a space of constant negative curvature, then this function s square chi takes on the form L square sine hyperbolic square chi by L. Okay. So, in the curved cases, you have these different forms for this function s square. The fact that the space is curved is important only when chi is of the order of L. When chi is much smaller than L, both these functions, all these functions reduce to chi square. Another point to note is that in the model, suppose, okay, how do we calculate chi? Let me just first address this and come back to this point. So, the light is propagating in the radial direction from here to here. So, this line element is 0 along that, and in the radial direction we do not have this. So, d chi is equal to c dt by a, or chi is equal to c times the difference in the conformal time between the emission and the observing of the light. And I have shown you that this could be written in terms of the Hubble parameter, which can be written as a function of the scale factor. So, this can be written in terms of the Hubble parameter as this integral. The integral is from the scale factor when the light was emitted to the scale factor when the light is observed, which in this case is 1 by 1 plus z to 1. So, given the Hubble the functional, so the Hubble parameter depends on what we believe are the constituents of the universe. Given those, we can calculate this value of chi. Now, suppose we have the same value of chi. For the same value of chi, the value of s square is going to be smallest for this model. Okay. In this model, the value of s square has an upper limit. This radius, this is like the radius of a sphere drawn around the, or this is like the this, you see, in Euclidean space, the surface area of a sphere is 4 pi into this r square. In non-Euclidean space, the surface area of the sphere is determined by this function. It is 4 pi times this, whereas the radius, this radial direction, it is chi. So, this ratio of the area of the sphere to the radius, this becomes different in non-Euclidean space. And when I have positive curvature, the maximum value that this function s can assume is L square. So, s can assume L, or s square can assume L square, because sine square can assume a maximum value of 1. So, it starts from 0 when chi is 0, and then it reaches a value L square, and then as chi increases again, it again proceeds towards 0, and that is the other. So, it is like a sphere. It is like you start from one pole, maximum value is the equator, and then as you move further and further away, the radius again shrinks to the other pole. Okay. So, this, in this model s increases the slowest. Here it increases faster than this, and this is the fastest. So, for the same value of chi, you will get different values of s depending on which geometry you are in. Now, having introduced all of this, we considered first the angular diameter distance. This is the ratio of this length to this, okay, other way around. The question is, what does an object of length L, what angle does it subtend to an observer? And this angle delta theta is this length divided by the distance. This distance we call the angular diameter distance. So, if you know the angle and you know the angular diameter distance, you can calculate the length of the object, or if you know the length and the angle, then you can calculate the distance to the object, whichever way you like. So, the one way in which you can, this can arise is that you know the redshift of the object. So, from the redshift you calculate the angular diameter distance, you measure the angle it subtends sitting on the earth, and then you can determine the size of the object. Okay, this is one possibility. And in the last class, we calculated the angular diameter distance. It came out to be s corresponding to that z from which the light is coming, divided by 1 plus z. Okay. So, we have calculated the angular diameter distance in the last class, and it has this form. So, let me not repeat the calculation. What I will do now is I will show you a few examples which I have worked out, and it will illustrate for you the behavior of these functions that we are talking about. So, we are going to consider 4 models. I have given them some names. Some of these names are the standard names that I use, some of them are just arbitrary. I have given them for the purpose of this class. So, the first one is the SCDM. This was a model, cosmological model, that this is a cosmological model that was once considered the favorable, the model, but now it is ruled out more or less. So, in this model, all these models have H equal to 0.7. This parameterizes the Hubble parameter. In this model, there is only matter, dark matter, which is cold. Okay. So, let us forget about this cold business for the time being. There is the usual pressureless matter, which has omega matter naught equal to 1. So, in our model there are 3 possibilities. I should first mention this. There is matter, then there is curvature, and then there is the cosmological constant or dark energy. Okay. So, the first model is what is called the standard CDM. This was once in vogue, but now it is ruled out. It has only matter, no curvature, no cosmological constant or dark energy. This model is spatially flat, k equal to 0. The next model that I have considered is a slight variation on this model. In this model, the omega matter is slightly more than 1. So, the sum of these 3 have to be 1. So, the curvature has to be negative. So, curvature is minus 0.1. There is no cosmological constant or dark energy. This model has k equal to 1, it is the positive curvature model. Okay. Omega curvature negative means that the spatial curvature k is positive. Okay. The third model, open CDM, OCDM, there are observations at present which indicate that omega matter is 0.3. So, this model has omega matter 0.3. If omega matter is 0.3, then the sum of these two has to be 0.7. So, in this model we assume that the curvature, omega curvature is 0.7. So, this has k equal to minus 1. It is an open cosmological model, hyperbolic, sine hyperbolic is the function, okay, negative curvature. Finally, we also consider LCDM, which is believed to be the model that our universe, that describes our universe, currently believed to be the model that describes our universe. Omega matter 0.3, universe is spatially flat, and the rest of it is in this cosmological constant or dark energy. Okay. Just to remind you what is the meaning of all of this. So, H as a function of A is H naught, omega matter naught A minus 3 plus omega curvature naught A minus 2 plus omega lambda naught. Okay. So, all that you have to do to calculate things in this model is that we have to put in this expression for H over here. Once we put in the expression for H over here, we get chi. L is determined by the value of omega curvature. I have already told you that L is C by H naught 1 by square root of mod omega curvature naught. So, you have to put in these and you can calculate S, you can calculate chi from the expression in terms of the Hubble parameter, and then you can just straightforward calculate S. If it is curved, then you have to calculate S in terms of sine or sine hyperbolic. If not, then it is just equal to chi. So, I have done this and I show you the results over here for these 4 models. So, for the same redshift, this shows you results for the redshift range 0 to 6. For the same redshift, for the same value of the redshift, this KCDM, which has got positive curvature, that has the smallest value of SZ, S. We expect it, I have already told you why. One of the reasons is that because it is sine, the other also the chi value itself is smaller. So, this has the smallest value. Now, the standard CDM model is slightly above this. It has got omega matter equal to 1, this has omega matter 1.1, and the LCDM and OCDM, open CDM, these values are much larger. Okay. Now, there is a redshift range up to roughly around 4, where the LCDM model has the largest value, the OCDM has a slight smaller value, but at higher redshifts the LCDM, OCDM takes over. So, this shows you the same thing on a log scale. Okay. So, this goes all the way up to redshift of 1000. So, at large redshift beyond around a redshift of 10, all of these curves more or less flatten out. This is increasing, but not very fast OCDM. So, all of these curves flatten out, KCDM is smallest, then SCDM, then LCDM, and finally OCDM. The one of the reasons why the OCDM model has the highest value is that with increasing chi, so with increasing look back time, chi is roughly equivalent to the look back time, because it is eta minus the difference in the conformal times. S increases as sine hyperbolic. Sine hyperbolic is exponential, right. So, it is an exponential increase in this case. Here it is just a linear increase. Here it is an increase, linear increase to start with, then it slows down. Okay. So, with increasing chi, S increases exponentially in this case. So, the OCDM model, the spatial curvature plays an important role and increases the value of S. For these models, I have also calculated the angular diameter distance. So, in the last class I had told you that the angular diameter distance has the property, angular diameter distance has this expression, it has S on the numerator and it has 1 plus Z in the denominator. So, it has the property that initially it will increase, it increases linearly and then it slows down and then it finally falls off, because this increases faster than this, right. So, I have shown you the values of this angular diameter distance as a function of redshift for all of these models. So, it reaches a peak value somewhere over here between 1 and 2 and somewhere around 1, 2, 3, somewhere over there it reaches a peak value 1 and 2 and then it falls off. So, if I take an object of the fixed size and I move it to higher and higher redshifts, the angle subtended will initially fall off, but once it crosses this value the angle will again start to increase. It is a very interesting thing that happens in this non-Euclidean geometry. This shows you the same thing on a log-log scale over a large range of redshifts. So, as you keep on increasing the redshift, this falls off further and further. Okay. So, we have seen how the angular diameter distance behaves. Now, next we shall consider the behavior of the luminosity distance. So, we shall take up the behavior of the luminosity distance. So, let me introduce first what is the luminosity distance and then we shall discuss its behavior. What? Okay. So, the luminosity distance is defined through this relation. There is a source of luminosity L, there is an observer at distance, at some distance. The observer, so the luminosity tells us the energy that comes out from the source in 1 second. The observer sitting over here, let us say here, cannot directly measure this. What the observer can measure is, what the observer can do is, he or she can place a detector and find out the amount of radiation energy coming per second into this detector. So, we assume that the detector has a unit area 1 meter square, 1 meter by 1 meter. So, the flux is what the observer can measure. So, the flux is the amount of energy that comes into this 1 meter square area detector. So, the aperture of the detector is 1 meter square in 1 second. This is what is called the flux. And in the Euclidean or in any geometry, the energy that comes out from here gets distributed over a sphere of radius 4 pi into this distance squared. So, the flux is the luminosity divided by 4 pi distance squared. Now, in non-Euclidean geometry, in the cosmological setting, this distance will be different from the angular diameter distance or the proper distance to this object. So, we call this the luminosity distance. I had also told you that you can have two kinds of definition. One is in terms of the specific luminosity. The specific luminosity L nu tells us the amount of energy that is emitted in the frequency interval delta nu at a time in a time interval delta t. So, this is the energy emitted in this frequency interval in this time interval. Similarly, we have the specific flux. You could also define the bolometric luminosity. The bolometric luminosity, the frequency information has been lost. So, if the radiation that is being emitted looks like this, some hypothetical situation. So, the source emits radiation over a band of over a range of frequencies, and this the specific luminosity tells us the amount of radiation in a small range of frequencies like the one shown over here, whereas the bolometric luminosity tells us the total energy emitted over the entire frequency range. Okay, a bolometer is a device that measures the total energy emitted, total energy incident on it. Okay. It may not be the total, it may not span all the way from radio waves to X-ray, but it at least it covers a large, considerably large frequency band, so that the bulk of the energy is quantified. Okay. So, we have two definitions based on these two objects that you can measure. So, let us first discuss the luminosity distance based on the specific luminosity. So, for the purpose of calculating this, it is convenient to redraw the picture. Let me do it. So, this is my source, the distant galaxy, and the observer is over here. And the light propagates. So, this is the origin, and the light propagates from here to here. Okay, let me put in a different color. So, the light propagates from here to here along the chi direction, radial direction. So, the light propagates from here to here. This corresponds to chi equal to 0, this corresponds to value chi. Okay, so, the light propagates from here to here. Now, the luminosity, the light source has a luminosity L. So, the amount of radiation that comes out, delta E nu, is L nu delta T. This I have already told you. Now, here you see the radiation is not conserved, the energy is not conserved. In the usual Euclidean space where there is no expansion, the energy is conserved. The same energy that is emitted here will pass through this sphere in some time. Right, here there is a different, there is an extra complication. The extra complication is the redshift. So, by the time the energy that was emitted over here reaches here, it has got redshifted. Okay, so, the amount of energy is obviously not conserved, the frequency has changed. So, we cannot actually deal with this directly, it is not very convenient. What is convenient is to think of it in terms of photons, particles. Okay, so, we know that the light actually propagates in terms of photons. So, let us calculate the number of photons emitted in the frequency interval delta nu. So, we will put nu emitted here everywhere. Okay. So, in the time interval delta t emitted, in the frequency interval delta nu emitted, it emits this much radiation. So, the number of photons n nu emitted. So, let us ask the question, how many photons are emitted by this source in the frequency interval delta nu emitted, in the time interval delta t emitted. So, how do you calculate this from the energy? You just divide it by the energy of a single photon. So, this we know is h nu. So, we have to divide L nu emitted, delta nu emitted, delta T emitted by H nu emitted. So, this is the number of photons which is emitted in a time delta nu emitted, delta T emitted in the frequency interval delta nu emitted. Okay. Now, the photons emitted from here will all cross this surface. Okay, they will all cross this surface, but the time interval in cosmology, the time interval at which they are emitted is not the same as the time interval at which they reach here. This we have already calculated. Not only that, the frequency interval at which they are emitted is not the same as the frequency interval at which they will reach this surface. So, all of these get changed in cosmology. So, let us first calculate what is the time interrelation between these. So, we know that the emitted frequency by observed frequency is equal to delta nu emitted by delta nu observed, which is equal to delta T emitted, other way around, delta T observed by delta T emitted. The frequency and time are inversely related. So, this is going to be observed by emitted, and this is equal to, so the frequency scales as the inverse of the scale factor. So, this is going to be A observed by A emitted, and the numerator we have chosen to be 1. So, it is 1 by A emitted, which is also 1 plus Z, the redshift. So, we know this. So, the time interval, the frequency interval, they are all related by this. Now, let us calculate the flux that will be observed by an observer at this point. So, an observer, the observer O over here, please keep this picture in mind, the observer O over here will observe. So, how many photons? So, this observer will observe the same number of photons. Photons do not get destroyed as they go from here to here, they are only their frequency changes. The rate at which they are emitted and the rate at which they are received are different, but the photons do not get destroyed, all photons emitted here reach here, that is what we are assuming. So, the photons, the number of photons that will be observed by this observer is the same N nu e, sorry. So, the number of photons that will be observed, let me just get rid of this, is N nu e, that many photons. They will now be observed over a time interval delta T observed and frequency interval delta nu observed. Now, these photons will each carry energy. So, in the time interval, this is the rate, in the time interval delta T observed, delta nu observed, these many photons will cross. They will each carry energy H nu observed. So, that is the energy that crosses this sphere in the time interval delta T observed, delta nu observed, where the delta T observed and delta nu observed are related to the emitted and time and frequency through this. Okay. And all the energy will be distributed over this sphere, the area of this sphere. Now, the area of this sphere is 4 pi into, so we want the physical area. So, the question is, what is the area of this sphere? So, the area is obtained by integrating the solid angle. The radial direction does not contribute to the area. So, the area is this S square into 4 pi, that is what you will get when you integrate overall solid angle, into the scale factor squared. That is the physical dimension of the area, the proper dimension of the area. So, what we have then is this will be divided by 4 pi a squared S square. This will give me the observed flux observed at the frequency nu observed, because the radiation will be observed at a different frequency, right. So, the flux will be observed at a different frequency nu observed, and this is equal to the number of photons emitted divided by the time interval over which they will be observed and the surface area multiplied by the energy of each photon. Okay. Now, the number of photons that are emitted is given over here. So, what we see is that this is equal to, the flux is equal to, I have the luminosity L nu emitted divided by 4 pi. This A is the value of the scale factor when the observation is done. The light propagates from here and it is distributed over a sphere whose size is 4 pi a s square, whose area is 4 pi a s square, and the size A, value of A is at the epoch when the light reaches here, which is at the present. So, the value of A that occurs over here is A0, which has a value 1, right. So, I do not have to bother about it. So, this is going to be 4 pi s square. So, I have put in the luminosity, I have put in the factor of 4 pi s square, this A is 1, and now this n also has the interval of frequency, interval of time, and the frequency. So, I have delta nu observed by delta nu emitted by delta nu emitted by delta nu observed, delta t emitted by delta t observed, nu emitted nu observed by nu emitted, all these factors. Okay. Now, we have already worked out what the relation between these ratios are, and we see, so that is given over here. So, we see that they are related to the redshift in this way. So, the point to note is that the way in which, so this ratio is exactly the inverse of this ratio, the time interval and the frequency interval, they transform as the inverse of one another. So, these two numbers exactly cancel out. So, these two numbers together give 1, and we have then the ratio of the observed frequency to the emitted frequency. So, the observed frequency is smaller than the emitted frequency by a factor of 1 plus z. So, this we see is L nu emitted by 4 pi s square 1 plus z. Okay. So, we have worked out the relation between the flux, specific flux, and the specific luminosity. Now, next thing is to identify the luminosity distance. So, the luminosity distance is defined through this relation. It is the quantity that relates the flux to the luminosity. So, what you see from here is that the luminosity distance is s into the square root of 1 plus z. Okay. So, the dl is S into 1 plus z to the power of half. So, this is the luminosity distance calculated using the specific luminosity and the specific flux. So, we see that it is equal to S, which we have defined, that is the tangential distance, into the square root of 1 plus z. Now, let me also determine the relation between the bolometric quantities. So, let us work out the bolometric case. So, the bolometric flux is the integral of the specific flux observed d nu observed. This integral, if I integrate over all observed frequencies, I will get the bolometric flux, and we have seen that this is equal to, we have already worked this out in terms of the luminosity. So, this is then the integral L nu emitted by 4 pi S square 1 plus z d nu observed. Right, I have just replaced the flux in terms of the luminosity. Now, we also know that the bolometric luminosity is the integral of the specific luminosity over all frequencies. Now, I have to be careful, you see, because this has to be integrated over all observed frequencies. L, I know L as of, this is related to the specific luminosity, but not at the same observed frequency, but at a emitted frequency, at a different frequency. So, when I do this integral, the variable should be the same, the frequency variable should be the same. So, since I know this in terms of the emitted luminosity, then I should write it in terms of the emitted luminosity. I could equally well write it in terms of the observed luminosity. I should write it in terms of the emitted luminosity. So, this gives me the bolometric luminosity. Now, here I have L as a function of the emitted frequency and I have d nu observed. So, I have to convert this to d nu emitted and then I can replace it with the total bolometric luminosity. Now, that is very straightforward. We have already worked out how the observed frequency and the emitted frequency are related. So, this is equal to, I can take all these constant factors outside, 1 by 4 pi S square 1 plus z square whole square L nu emitted d nu emitted. And this is the total bolometric luminosity. So, finally, we have this expression that the bolometric flux is equal to the bolometric luminosity divided by 4 pi S square into 1 plus z whole square, or the bolometric luminosity distance is S into 1 plus z. It increases faster than the corresponding quantity if I use the specific luminosity instead of the bolometric luminosity. So, let me summarize the three distances that we have calculated. There are various other distances also which could possibly be of interest depending on the situation. We have calculated three. So, the first is the angular diameter distance dA. This is the coordinate distance S into 1 plus divided by 1 plus z, the specific this is the luminosity distance based on the specific luminosity, and we also calculated the luminosity distance based on the bolometric luminosity So, we have calculated these, we have got expressions for these three distances. Let me now show you, I have already shown you how the angular diameter distance varies with redshift. Let me just show this again. The angular diameter distance, it initially increases with redshift, and then beyond the redshift, beyond a certain redshift, the value starts to decrease and it tends to 0 as you go further and further away. So, this is the property of the angular diameter distance. So, you take a fixed ruler 1 meter, let us say, or whatever size, fixed size. If you move it further and further away, it will get smaller and smaller, but beyond a distance it will again get larger and larger. Okay. Now, the luminosity distance I have shown here, the bolometric luminosity distance based on this bolometric luminosity. This has the property that it increases monotonically with redshift. The higher the redshift, the larger is this luminosity distance, or the fainter the object is. So, this shows you the luminosity distance as a function of redshift. Again, we have these 4 models, the KCDM, SCDM, then we have the LCDM and the OCDM. So, at redshifts around between 3, 4, the LCDM gives you the furthest distances, OCDM is slightly less, and the SCDM and KCDM are much smaller. Okay, you could vary. I have only shown you 4 cases. You would actually have a continuous set of curves. I have just varied the matter parameter from 1 to 0.3 abruptly, right, but you will actually have a whole set of curves if you change the parameters gradually. Okay. So, if I had a fixed object of fixed luminosity, and if I were to move it further and further away, it would get progressively fainter and fainter. Now, the same object at the same redshift would be fainter in a LCDM universe than an OCDM model or a SCDM model. So, same object, same redshift, the predicted flux would be smaller in LCDM at these redshifts. Okay. Here the OCDM model would be faintest. So, okay, so this is the point, this is the implication of this graph. This shows you the same thing, the luminosity distance, the defined through the bolometric luminosity over a large range of redshifts all the way to 1000. Okay. So, what have we done? I have told you how you could calculate these angular diameter distances and the luminosity distance, which are very useful when you want to interpret cosmological observations. Okay. So, I have shown you how to calculate these given a cosmological model. So, once you specify the model, you can calculate these. There is another very important role that these distances play. Let me explain this today, and we shall go into it in more detail in the next lecture. The other very important role that these distances play is as follows. Suppose I do not know, which is the situation, I do not know the cosmological model. Okay. So, there is no reason, there is no reason why I should, how why should there is no reason for me to say that this is the particular cosmological model that we live in. So, it is an open question, what is the cosmological model? So, determining so, the question is that we have discussed certain cosmological models. How do we decide what is our what is the model that correctly describes our our universe? So, to do this we have to match the predictions of the model against observations and see if they correctly predict the observed quantities. Now, I have introduced a kind of cosmological models, a class of cosmological models. These are not the only possible cosmological models. What we have done is we have considered a class of cosmological models. In this class of cosmological models, there are a few free parameters. So, these parameters are H naught, and then we have the omega I naught for different components. So, we have assumed that we have different components, each of which has a pressure which can be written as W I rho c square, and we have also assumed that there are a certain number of components. Okay. So, the simplest possible model which you could consider, you have omega matter naught, omega curvature naught, omega lambda naught, whose properties we have already discussed. You could also have relativistic particles, radiation and neutrinos, but they do not play a very important dynamical role in the at present. Okay. If you go sufficiently back in the past, for reasons which we shall come to, this is important only in the past, because it is multiplied by a to the power minus 4, which is a very small number now. Okay. This number itself is very small. So, we do not have to bother about this. So, this is a possible cosmological model. You could have other kinds of components, nobody really stops you. Okay. But there should be observational evidence which indicates the presence of such components, or there should be some theoretical motivation which prompts us, based on which we introduce such a component, which tells us that no such a component should exist. Okay. So, the question is, how do we determine all of these things? How do we determine the value of H naught? How do we determine what are the components present, and if so, what are their contribution relative to the critical density? So, one possible method is based on these distance measures. The Hubble parameter you obviously will determine from distances. You determine, so the way Hubble did it was he directly determined distances and he determined redshifts, and Hubble found that they had a linear relation, which we have seen is true at small z, and I have not shown it for some of the cosmological models. I have not shown it, but you can easily verify that it is true for all cosmological models at small redshifts. Okay, it is easy to verify. So, you have to just take the expression relating the redshift to the distance and work out what it implies for small z. You will find that they all imply the same thing. So, at small z, they all imply that the distance, whichever distance you use, is equal to C z by some constant H naught, and you can use this linear relation to determine H naught. Okay. But as you go to higher redshifts, the curves are no longer linear. So, it depends on what distance you are measuring, and it also depends on the values of these cosmological parameters. Now, question is, how will you determine the distances to distant objects? all that you can measure, let us say angular diameter distance, you want to measure the angular diameter distance to different objects. You want to measure it, not predict it from your model. You want to measure it. So, the basic idea is that you measure dA, the angular diameter distance, okay, and then you compare with model predictions, which we have seen how to calculate, and this will tell you whether which is the valid model, what are the values of the parameters. So, here we could take up a model which has these 3 parameters. So, for different values of the parameters you will get, and this you will get different dA for the same redshift. So, you have observed an object for which you know the angular diameter and the redshift. Now, your model will again do the same thing for a given redshift, it will predict the angular diameter distance, compare this with this, see if it matches. So, you find out the set of parameters which give the best match to the observed data. Okay, so, this is one way in which you can determine which cosmological model you are. For this you need, so to do this, to do this using angular diameter distance, you need what is called a standard ruler. A standard ruler is an astronomical object whose physical length is known, whose length is, whose size, physical size is known. For example, a galaxy we know is of the order of 30-40 kiloparsecs, okay, but there are variations, but we have some idea. So, if you use a galaxy as a standard ruler, there will be certain variations. We do not see galaxies which are say a fraction of a parsec or something like that. Okay, so, spiral galaxy we know that its size is of the order of tens of kiloparsec. Okay. So, the more precise, so suppose you find some kind of object whose size does not have much variation. So, wherever at whatever redshift you see it, you can be sure that its size is this L. Okay, so, it is an object whose size L is known for some reason or the other. If you know that objects only occur with a certain size L, then if you can measure the angle delta theta, that can be measured in astronomical observations. So, dA, the angular diameter distance, will be L by delta theta. So, to do this test with angular diameter distance, you need a standard ruler. So, it is like putting a 1 meter ruler stick at different redshifts, and then you measure the angle it subtends. Once if you can do that, L is fixed, you measure delta theta, then you get the angular diameter distance. So, if you can do it for different redshifts, you will get angular diameter distance as a function of redshift observed, compare it with the model prediction. Okay. And some models will not be able to predict. So, each model makes a different prediction. Okay. So, if you compare with predictions, you can say which model is correct, what are the values of the parameters. Okay. Similarly, you could also do this using luminosity. So, what you need what is called a, so with the luminosity distance, so you need what is called a standard ruler, a standard candle. So, if you can identify certain standard candles, these are objects, astronomical objects whose luminosity, again L, okay, little confusion, but whose luminosity is known a priori. So, we know that spiral galaxies have 10 to the power 11 stars. So, the 10 to the power 11 solar luminosity of that order. So, this is an example, does not serve as a very good standard candle because there are variations. So, this will introduce for the same redshift, if you have a brighter galaxy, you will get a different angular luminosity distance, etc. Okay, so, a standard candle, a good standard candle is an is a class of astronomical objects whose luminosity does not vary wherever, at whatever redshift, wherever you see it in the universe. If you have reason to believe that its luminosity does not change with z or position, then you can use it as a standard candle. So, for a standard candle, if you can measure the flux f, you measure this, could be bolometric or could be specific. You measure the flux, and the flux is the luminosity by 4 pi dl square. So, this gives us dl, and if you can measure dl as a function of z, again the model predictions are different, each model makes different predictions. So, if you can measure this as a function of z and then compare it against the model predictions, you can then say which cosmological model is the one which, or the class of parameters which are consistent with these observations. Okay. So, this is a very important application of these distances, and I shall discuss this in the next class.